possibilities, combinatorics, and factorials, and permutations, which I forgot to write here. I'm going to be using permutations to later explain combinatorics, which gets really important later, especially in probability when using the classical method, when you know how many outcomes there are, and you want to see how likely an outcome is, but we'll get to that later. So permutations. As opposed to combinations, the order matters in permutations. And combinations are nominal, meaning that the order does not matter. Permutations are ordinal, so they do matter, and they do have weight, meaning all that means is that the order has significance. And I can explain it using a real world analogy. So let's say we're trying to make a team of 3, and or a team of 2, and we have the options A, B, and C. It doesn't matter if we have a team of A, B, or BA, right? Because AB is the same team as BA. The combination and the order does not matter. But let's use a permutation, for example. And let's say that we have a race, and we want to know who the top 3 winners are. A being first place, B being second place, and C being third place is not the same as C being first place, B being third place, and A being second place, because third place and second place aren't the same, and second place is not the same as first place. So that's all that means, and we'll get into permutations with repetition. So let's explain how this works. And we can read this all here. However, I'm going to explain it really quickly using Sketchpad to understand why it works, because I hate when you're just blindly given a formula and expected to understand what it means. But these are the easiest to calculate. And when a thing has n different types, we have n choices each time. We use this when we can reuse answers. So repetition is the same as replacement, which simply means you're replacing the thing you chose. So let's say you have a deck of cards. And let's say that we take a card out of the deck. To replace for the card that we took out of the deck, we put the same card in the deck. And this is simply so we can keep it consistent. But it's a little bit hard to explain here, so I'll explain it in a second. So let's say we have A, B, C, and we want to make permutations with a repetition of 3 positions. That means we can use A, B, or C as many times as we want. So the first letter is A, we have 3 more possibilities, A, B, or C, and then those each have 3 more possibilities. In short, n to the rth power, or the number of our data set to the power of the size of what we are trying to make. And that's the simplified version. And you won't really find that anywhere, so you can watch my video for that. So we have A, B, and C. And let's say we're trying to see how many different permutations we can make, because we're dealing with permutations. For example, and I'm just going to go over it real quick, A, B is not the same as B, A in permutations, but combinations treats them the same. So that's all the difference is. For here, permutations would consider these 2 different outcomes. Combinations say they are the same. Combinations are for if it's nominal, meaning the order doesn't matter, or like the weight doesn't matter. But like in a race where first place is different from second place, all the orders matter. So it's important to note that. So let's say we have ABC here. And someone says, if we were to ask a random person, and let's say these are just ice cream flavors, right? And if someone says, if someone were to pick these ice cream flavors at random, how many different random possibilities can we make with this? So let's just say this is, actually no, I'm not going to give them flavor names because that'll make it slightly more complicated. So all replacement means is that we can reuse the options. So for A, B, and C, let's say that we couldn't replace it, and all that means is if we choose A, we can't use A again because it's used up. You can't pick an ice cream flavor again if you've already picked it. However, if we can pick our favorite ice cream flavors, for example, and we can pick one as many times as we want, then we can replace it. So what does this mean in terms of logic? Because math is just logic, as we know, and math is just another language that we express things. All this means is that the number of choices stay consistent no matter what we are trying to do. It sounds a little bit complicated, but here we'll explain it with numbers here. So when we choose what we want in our first position, or if we're just choosing at random, we have three different possibilities. I could choose A, B, or C. Now, if we choose A, for example, we have another three options. Note that the number of options did not change. If we chose A, that opens up three more options, A, B, and C. Replacement says that we cannot pick A again, so then that would be 3 times 2, because now we only have 2 options. But since we have 3 independent options, and then each of those options have 3 again, because you can choose whatever you want again. These are the options that you'll be stuck with, and that's why it's n to the rth power, because the number of options that you have at the beginning does not change within each step, meaning that if we choose A for the first step, we can choose A, B, or C again. So simply put, we have the same number of options as here. So each option leads to 3 more options. And these options lead to 3 more options if we're choosing more than 2 steps here. So simply put, the probability stays, or the number of options stays the same each time. So we only use this 3 to the rth power, and 3 just replaces n here because it's the number of frequency, or how many options we have. And r is what we're trying to make here, and we're trying to make a group of 2. We're trying to arrange them in groups of 2. So it becomes 3 to the second power, which is 9. And that matches up. If we choose A and A, we have the AA, AB, AC, and then right here we have BA, BB, and BC, and CA, CB, and CC. Note that, sorry, it's a little bit messy. Note that these are all the possible positions. So if someone were to choose this at random, it would have a sample space of 9, which I explained sample space in 5.1, I believe. But all that means is that the number of available options would be 9, which would be any of these 9 here. So trying to get into the logic of how it works is a little bit complicated, but I understand it. I know it's a little bit hard to put into words, but each step we have the same number of options, and since R determines how many times or how many steps we take, so here we have 3. So if we only chose, and let's erase this, and we're trying to make groups of 2. If we chose, let's make groups of 1. Here, if we were to choose a groups of 1, we can either choose A, B, or C. We have 3 options. That means if we were to choose one of them randomly, we would have a 1/3 chance of being selected, since it's random and each of them are equal probable. That's simple random sampling if you don't know. However, since we can replace each one, and if we want to do steps or groups of 2, now it opens up 3 more options. It could be AA, AB, AC. So we do it to the rth power simply because each one opens the same amount of options. So it'd be 3 times the number of options we have, because each individual step here has 3 more options. And if we use this discretely, like X, Y, comma, Z, we have 3 options here. And each one opens X, Y, Z. And I know it's the same discrete. We're just using different variables here. So each one opens the same amount of steps. So it would be 3 times the same amount of steps for each one, which is 3, because each group is 3. This is the same as 1 times 3 plus 1 times 3 plus 1 times 3, because each one opens individual steps. And then each of these will open another 3 steps, because each one opens up another 3 and another 3 steps. It's a little bit complicated, but I hope you understand the logic behind it. And you can ask me any question you want if you still have some. And it's really hard to understand. For me, it took a while, especially because I want to learn how everything works. So that's what happens there. So let's go to permutations without repetition. And for me, this is a lot easier to understand. Or for like the basic people. For basic understanding. And in this case, we want to reduce the number of available choices each time. And this one is a little bit easier to understand simply because it happens in real life situations. So let's say we have 1, 2, 3, 4, 5. And we want to pick first place, second place, and third place. This is a race. So if we choose 5 here, 5 cannot be second place again. So now we only have 4 available options because once we use 5 up, we can only choose 4. And then if we use 4, we can only use 3. And then if we have 3, we only have 2. And this is, sorry, that was dumb using numbers because it's a little bit hard to understand. But let's say we have A, B, C. If we use C, we can't use C again for the second place. So now we only have 2 available options. So that means we can rewrite this as C, and then we could choose A or B. So C times 2 because each C option gives us 2 other options. And then once we choose A, each one only has another option here. So if we choose A, then B would have to be third place, and if B is second place, A would have to be third place. So if we can see here, C has 1 outcome, but that multiplies to 2 because 2 options come out of 1 option, and then each one yields 1 individual option itself. It will be C times 2 times 1, or 3 times 2 times 1, simply because we had 3 options at first. So we had C times A times B. And if we chose A, we would have B and C. And then we would have A and, we would have C and B. And then here we would have the options again. So we do something here called a factorial. And a factorial is really easy to understand. So we have n factorial. And that's simply n times n minus 1 times n minus 2 times n minus 3. So we'll explain this easier using actual numbers. 3 factorial is the same as 3 times 3 minus 1 times 3 minus 2, and then not 3 minus 3 because that would make it 0. So here we have 3 times 2 times 1, which is 6. And permutations are really important in the field of mathematics, obviously, but really in the terms of calculating probabilities. And I forgot what the notation was. I know what the formula is. Okay, I guess there is no notation. I know in combinations it's NR. But here we'll just write the formula down. And it's n factorial n minus r factorial. Now let's explain why this works. Let's say we have 10 options, right? And that will be A, B, C, D, E, F, G, H, I, J, K, all the way until there are 10 options. If we choose 1, now each one can only choose 9 more. And sorry, this is actually a really bad example because it's hard to conceptualize. So let's use the terms of A, B, C again. And we have 3 options here. If we choose A, now we can choose B or C, and then we could choose C or B. Because if B is second place, C is then third place, and if C is second place, B is then third place. These are 2 completely different outcomes. And let's just go back to the explanation. So we have 3 options here. And regardless of what we choose, so we have 3 outcomes here, each one will only yield 2 outcomes because we cannot reuse each one. So because A, you can only choose B or C, those only have 2 options. And then we lose 1 more option when going from 2 to 1. That sounds really complicated. All that means is that because you can't reuse things, the possibility lessens by 1 each time. So we can make that whole tree diagram again, but I'll just explain it here. And n right here is going to be the number of the frequency or the amount of things we have in the data set, and r is going to be the amount of order we want. So if we want groups of 2, then we can rewrite this as 3 factorial 3 minus 2 factorial, which is just 3 factorial, which is 6. So it's a little bit hard to understand, But it's important to note that we use the n minus r thing, and I'll explain how that works just now. So let's say we have 5 options, and we'll denote this as A, B, C, D, E. If we choose A, that opens up 4 options, which are going to be the other 4 options here. If we choose B, it opens up the other 4 options, A, C, D, E. If we choose C, that opens 4 options, A, B, D, E. 1, 2, 3, 4, E, 1, 2, 3, 4. So if we start with 5, because of the 5, 1, each individual 5 has 4 options. And if we write this down again, B, C, D, E, now this one only has C, D, E, and 3 more options. And each one only has 2 more options. So we go on, and so forth, until we get a factorial. This looks like a factorial. And because we lose 1 option each time, we have 5 groups. Each group contains 4 options. Each of those 4 groups, which will be 20 groups when we do the math, have 3 options. So 20 groups have 3 options, which will give you 60 options. Then we have 2 more options and 1 more option. So that's how it works. But we use the n minus r correction term simply if we want to remove how many options we take. So let's say we only want to make groups of 3 here. And let's rewrite this tree diagram. Wow, it's going to take a long time. Okay, let's say we want groups of 3 here. And we'll only be doing the tree diagram for 1 because it is really tedious. So, okay, you get it. I'm not going to write the letters, actually. Wait, sorry. That's actually wrong, by the way. There we go. We have B, C, D, E. So if we choose A, we can't use A again because it's not replacement, and we have the options B, C, D, E. So that means 1 group yields 4. But we have 5 groups, so that would be 5 times 4, because each group yields 1 more. And then each group yields another 3, because we can't reuse options again. However, the issue is that the n minus r correction term is used simply because we don't want to evaluate this combinatorial all the way, or this permutation all the way. Because each of those 3 options have another individual 2 times 1 option. However, we don't want to do that all the way, and it's a little bit complicated to understand. So, yeah, we don't evaluate it all the way simply because we only care about the first 3 options. And the first 3 options are decided when we have each of the 3 paths chosen. It's a little bit hard to understand, but I hope you get the logic behind it because it's really hard for me to say in words. So, here's the formula. Combinations without repetition. And I love this formula because I understand how it works. And it took me a long time, so it's just really complicated. N minus r factorial. And I hate explaining how it works, but I guess we'll have to do it again. So let's say that we want to make 3 groups, or we have 3 A, B, C, and we want to make groups of 2. If we evaluate this combinatorial out, and 3 is the frequency, over 2 factorial times 1 factorial, which is simply going to be 3. Because we can make 3 different groups of A, B, AC, and then we have BC. So these are the 3 different outcomes, and we can prove this formula works. So the R factorial correction term is simply because that's how many ways we can rearrange probability. So let's say we have, sorry, I just deleted it, AB, AC, BC. The R factorial is the number of boxes factorialed, right? So number of factorials gives us the option. So if it's 2 boxes, then we can rearrange them 2 times because we can flip them around. If it's 3 boxes, we have three options at first. A can go in this box, A can go in this box, A can go in this box. And then you have two more options. B can go in that box, B can go in that box. And another possibility, which is already set because the degrees of freedom are less. It's a little bit hard to understand, but I hope you get the logic behind it. So, yeah. So this is why we include the R factorial term. It's a little bit hard to understand, but it's just super hard to conceptualize. And yeah, I hope you can use this to understand what it is, but all the formulas are going to be left here, so